today, Professor William K. George. He did his undergrad from Johns Hopkins University in 1967 in engineering physics, his PhD in mechanics from Hopkins as well in 1971, and then under John Lumley. And then he started his career at Penn State in 1968. As you probably have known, he's very well known for his theoretical and experimental work in turbulence. He started after Penn State, he went to UB, SUNY Buffalo. He was there over 20 years. In fact, that's where I met him. And he did his PhD, he was there until 2000. He's currently the Professor Emeritus at Chalmers University in Sweden. And he started there as a professor of turbulence. He's also a visiting professor at Imperial College in UK. And he held the EU Marine Curie Professor. He's a fellow of the American Society of Mechanical Engineering, fellow of the American Physical Society. Among some of the awards that he has received, we could name many, but we're gonna name just few, including the Freeman Scholar Award from ASME. He's also the Distinguished Research Fellow of the British Royal Engineering Academy. In 2013 to 2014, he was the William K. Professor of Distinguished in Teaching at Princeton University. And very recently, I was studying a book, and the great Sir Isaac Newton wrote, "If a man can see further, it's because he had stood in the shoulders of giants." And indeed, we have today a giant, and there are many good reasons for that, but one of those is because I will not be here today if we don't have a giant like Bill George. So welcome, Professor George.
One of the greatest joys of getting old in this profession is watching the success of your students. And it's really an honor to be introduced by a former student. And I have another former student in the audience. So I realize not only that I'm getting old, but at least maybe something I've done in my life was a success. So, and it's a special honor to be in this university. I said it's the only university I know of where the president of the university actually wrote a column in the Washington Post advocating a solar and wind generator wall along the Mexican border. And I'm sure that cost him something politically, but it showed remarkable courage. So I'd like to at least acknowledge that. It's nice to be here. Actually, one of my very first talks after I finished my PhD was here at Purdue. I almost didn't make it. I went to visit my relatives in Illinois and then rented the car and drove here. And I was an hour late, arriving just in time for my talk. Those of you who know about in Indiana in summertime know very well what I was talking about, but I nearly missed my talk. And speaking of relatives, it's a real honor to have two of my relatives in the back row. I just met my niece for the first time, who's a freshman here. She should be studying for physics, and my brother-in-law, Tom Patton. Originally, I proposed Tom would give a magic show, but I think Luciana was afraid there was probably enough magic in my talk for everybody. Tom was a coordinator for the Hammond schools here in Indiana for many, many years. You may even know somebody who went to school under his tutelage, so it's a real honor to have them in the audience as well. Anyway, I am not, my education was primarily as a physicist. Fortunately, I got an engineering degree, even though I never took an engineering course. That was sort of what was weird about Johns Hopkins at the time I was there. Unfortunately, the two things because of the Vietnam War, I had to leave rather early, which is how I ended up at Penn State before I finished my PhD. But unfortunately, the two courses I never took were quantum mechanics or general relativity. So prior to my interest in this problem, I can honestly say I didn't know a thing about either subject. So you should sort of take that into consideration about what I'm saying today. On the other hand, as my colleague and co-author Gunnar Johansson and I said in the postlude to the paper we just wrote, between us we have 100 years of research and moving from one field to another. Not 1 second of that 100 years has been spent in general relativity or quantum mechanics. And yet here I am talking about it today. I got interested in this problem about 5 years ago. I was on my way to Boston to the APS meeting, and we were running late, and there was a Canadian broadcast on the public radio. This program, I think, was called As It Happens. And they were interviewing three experts in the field of astronomy. And they were describing why scientists, and astronomers in particular, astrophysicists, believe in dark energy and dark matter. And as I listened, I began to realize, and I had never paid much attention to this subject other than as a layman and general curiosity. As I listened, I began to realize what they were describing was not a problem in quantum mechanics or general relativity. It was simply the failure of the mechanics equations to add up. And I think I said to my wife, these are the equations I'm supposed to be an expert in. So why don't I just take a look at it? And one thing led to another, and eventually here I find myself. About 3 years ago, I went back to Sweden, and my former colleague Gunnar Johansson and I, who retired at the same time I did, we decided, hey, look, let's sit down and see if we can teach ourselves quantum mechanics and relativity. Now that's quite a challenge, especially with COVID. But one of the wonderful things about now is you can learn almost anything on the internet. And you can learn it from the most famous people. If you want to learn about general relativity, you can tune in all the lectures from Susskind at Stanford, or Maloney at McGill, or you can listen to Goth or Hoff from MIT. I mean, it's just an incredible amount of resources out there. And then you've got things like, you've got these wonderful videos by Dr. Becky. If you found Dr. Becky on the internet, I mean, who's just a delightful postdoctoral student at Cambridge, or Oxford actually, who decided to educate the world about astronomy. So it's really a fun time to learn things on your own. And thanks to COVID, most of us didn't have any choice. That was about the only way you could learn. You couldn't go to a meeting, you couldn't go to a class. But anyway, it's been a delightful way to spend 2 years. And this is the result of that effort. So we'll see how it goes. Because Gunnar and I didn't have the ability to go to a university, we had to have all our meetings at the University of Coffee in Mölndal, Sweden. This is a delightful little coffee house with a wonderful name called Café Bullbrunnen, which means in Swedish, cafe bubbles. And it's this place, actually, the woman designed it so mothers with children or fathers with children, which is very popular in Sweden, come to the place, let their kids play and sit and have coffee. And they were very nice to tolerate these two old professors sitting there taking up their table and milking 1 cup of coffee for 3 hours while we discussed general relativity. I'm sure they all thought we were totally nuts. And made it clear they thought so, but they enjoyed listening to us anyway. But anyway, this is our university. If you're ever in Mölndal, Sweden, I hope you make a visit to Café Bullbrunnen. Okay, Luciano, tell me how to move. What do I do to move the?
Pressing. Yeah.
Press what?
Pressing.
Just click. Oh, that. I'll go on the computer. Okay, good. All right. Here's my assumptions about this audience. Number one, I assume we've all heard of Albert Einstein and Paul Dirac. I'm sure you've all heard of Einstein for sure. You'll learn a little bit more about Dirac by the time I finish. I'm assuming half of you know a lot about physics. There might be less than half, but I'm sure many of you do. You probably do know about Maxwell's equations and the equations for electrodynamics and quantum mechanics and general relativity. And the other half of you probably knows a lot about turbulence and fluid mechanics. But my bet is that half of you don't know what the other half know. So if you're like all the engineers I educated over the years. So what I'll try to do is I'll ask you, please be patient while I try to educate the other half, whatever it might be. So let's start. Here's what we're talking about. Now, this is a kind of a fuzzy photo of this famous deep space photo from NASA. And what's spectacular is those are galaxies. When I was at your age, those were nebulae. We couldn't even see most of them. We had no idea what they were. They were just kind of fuzzy spots on the camera. And each of those is a galaxy, many of them bigger than our own galaxy, the Milky Way. Now, just think about what this means. First of all, it means we are probably not alone, because there are literally billions of these things out there. Okay, that's the one thing. We're really talking about all of space. Now, let me warn you, many people think of space as, they say, well, we'll treat it as though it's infinite, but they think of it as finite. The space I am considering mathematically is one that's truly infinite. Okay, now, make sure I hit the right arrow. Good. There are actually billions and billions of these galaxies. And how should we think of them mathematically? Now, the laws of physics are presumed to apply to each one. They're presumed to apply to all of the stars and planets that might be among them. And the laws of physics are presumed to apply to literally every atom that is in these galaxies. Okay. What we are going to talk about, and what Einstein's field equations describe, is a continuum approximation to these. So you should think of these as like individual molecules in a gas. I mean, it's kind of mind-boggling, right? Each galaxy is like one molecule of the gas in this room. Right? Now, we know we can if we try to keep track of all those individual molecules, it's hopeless. We can't possibly calculate the mechanics of that. So we start making continuum approximations, right? We talk about pressure, we talk about density, we talk about temperature, which is related to kinetic energy. So that's a continuum approximation. And then we want to start talking about where these molecules go. And so we need a set of equations. We eventually evolve things like Euler's equation and the Navier-Stokes equation. And then we realize that, well, even that doesn't work because all these things are random and fluctuating. So we start averaging again. Okay, we've averaged over the molecules. Now we start averaging over the averages. And we really build up now a continuum approximation, which has millions of molecules in each little thing we call a fluid particle. Okay, and now we ended up with the Navier-Stokes equations, and we realized we can only solve that in very simple situations. So we average again, usually in space or time or both, and we end up with things like the Reynolds average equations or the LAS equations, depending on what you're doing. Okay, now that's exactly what we're going to do with cosmology. Imagine take a million or so of these galaxies and average locally all the ones in that neighborhood. That's a fluid particle. So that's exactly the analog of the continuum approximation we make if we work with fluid mechanics for turbulence. Okay? And then again, we're going to average, you'll see, we're going to average on top of that again. So it'll basically be an average of the averages over all the galaxies. Okay, and those are the equations we finally will be able to deal with. Okay, now what are these magic equations? Well, this was one of the great triumphs of the human mind. Einstein, back about the turn of the last century or so, spent 10 years evolving these equations. Now, the problem was the mathematics had barely existed. Einstein was not a very good mathematician, actually, so he had a lot of help. But when it was all done, he came out with these equations. And you say, oh, I've never seen such a thing. Well, actually, you probably have, if you've studied fluid mechanics. If you're a physicist, of course, I'm sure they've already taught you this. At least it's coming if you haven't gotten it yet. But if you take the divergence of this equation, you'll end up, the divergence to the left-hand side will disappear, at least the way I've written it down below. And the divergence to the right-hand side are the Navier-Stokes equations. So here, everything that we do in mechanics or fluid mechanics or engineering is basically in a very direct way related to Einstein's equation. Okay, so what is this equation? Well, the thing on the left is, on the right is called the stress energy equation. That's this piece right here. The R's are basically the Riemann tensor. If you take the trace of the Riemann tensor, you get the Ricci tensor. And you take the trace of that tensor, you get the Ricci scalar. Okay, so there's actually four things, one of which you can see. we can see the Riemann tensor, so-called Riemann tensor, this thing right here with 4 indices. You can see the Ricci tensor, and you can see the Ricci scalar. And this thing over here is where all the action is in a way, because this is where all the effects of mass and energy come into the problem. So the way Einstein imagined it, you put in the matter with whatever properties it has, energy or mass, for example, and it dictates how space deforms around it. And this, what this Riemann tensor is really, it's actually telling you how space deforms. It's actually a measure of the curvature of space itself as deformed by matter. Now, that was a great breakthrough, actually. And in fact, I've chosen to, well, let me tell you what there's some important things here. There are ideas you're familiar with, perhaps not in this context. There's something called the Jacobian. And the Jacobian is just a way of going from one vector space to another vector space. And by the way, let me tell you what these indices are. In fluid mechanics, we usually only deal with 3 indices because we treat time as separate. Physicists dealing with, in fact, with 4-dimensional space. So anytime you see a repeated index, if it's a Latin character, it means sum from 1, 2, 3. If it's Greek letters, it means sum over 1, 2, 3, 4. Okay, so it's not that hard, really. And the reason you have upper and lower indices, anytime you work in a non-Cartesian space, you need to identify really which set of, whether you're working with coordinates that transform the gradients or coordinates that transform vectors. And anyway, for those of you who understand that, that's great. If you don't, it doesn't really matter for now. Okay, but the important thing that comes out of all this is there's a quantity called the metric tensor. And it's the metric tensor that tells you really everything, pretty much everything there is to know about space. Because the metric tensor is really telling you how space is formed. In fact, we're going to see a lot of use for that metric tensor. There's a phenomenon called a quantity called the covariant derivative, and it's just like a gradient. The difference is a gradient doesn't transform in curvilinear coordinates like it does in Cartesian space. So if you want to transform it as a tensor or a vector gradient in curvilinear coordinates, you've got to take this special kind of derivative that adds a whole bunch of terms. I didn't put the symbol, but it's called a Christoffel symbol. One of my colleagues at Buffalo, Bill Ray, Luciano, and he used to call them Christ awful symbols, but they had 3 indices and they were incredibly difficult to write out. And if you work in polar coordinates or almost any problem with CFD, you're probably, you or the person who wrote the equations before you was working with Christoffel symbols. Because anytime you work with a non-Cartesian space, you've got to basically allow for the curvature of space. Anyway, so that's the covariant derivative. It's just the way of making sure those derivatives transform correctly. And so we've got all the ingredients here, and it was really Einstein's insight that realized how to interpret this gravity. And I can't do better than to give you a direct passage out of the book by Dirac, which he wrote back in the 80s, and one of his last lectures, a set of lectures at Florida. He says, at first sight, Einstein's law of gravitation does not look anything like Newton's gravitation law. To see a similarity, you have to think of this G mu nu as potentials describing the gravitational field. This, by the way, let me tell a joke. Luciano said I wasn't allowed to tell jokes, and I wasn't allowed to tell stories. But one of the great physicists of my youth, and it was a guy named Richard Feynman. He wrote some fantastic books that came out when I was a freshman. And they transformed my life, those books. But he was also a great jokester, and he won a Nobel Prize. And he tells a story about going to a meeting in Chicago. He was a professor at Caltech. And as I have done, unfortunately, myself, he shows up in Chicago and he had forgotten all the information about where he's supposed to go. And he had also forgotten to bring any money. I actually had that happen in Minnesota one time. Okay, so at least I knew where to go. So he goes to the taxi driver, and it's a meeting on general relativity. And he says to the taxi dispatcher at the O'Hare Airport, he says, I need to go to this meeting where all my colleagues are, but I've forgotten where the meeting is. He said, could you ask your taxi drivers by radio and see if any of them delivered a bunch of guys talking about G mu nu? So the dispatcher gets on the radio, and about that 3 or 4 taxi drivers in me, yeah, we've had a bunch of those nuts in our cab. So that's how he found out where he was supposed to go. Anyway, G mu nu is this classic way to describe the metric tensor. Anyway, what was neat is thinking of not as a space, but as potentials. And if you work with potential theory at all, I'll show you what I mean in a minute. Anyway, that was the great breakthrough. And what I wanted to really highlight in this is, says looking on the G mu nu as potentials, we find that this Einstein equation we saw above, they're like the usual field equations of physics in that they're second order, as Christoffel symbols involve first derivatives. They are unlike the usual physical equations like Maxwell's laws in that they are not linear. This is the key connection point with what we do in fluid mechanics, far from it. The nonlinearity means the equations are complicated and it's difficult to get accurate solutions. In fact, it's almost impossible to get solutions by just brute force. As many of you who work in CFT know, even in a computer with all the power we have, this is tough. Now imagine, think about what these equations look like. I'll go back one if I can. This equation has 4 indices each. So you got the indices are 0, 1, 2, 3, 4. This is 64 things. It's 64 equations. Now, unfortunately, there are a lot of symmetries that reduce the number, but we complain about having to work with 3, right? Plus continuity. This is 64 equations. You can see why there haven't been a lot of progress solving them. Okay, let's keep going. This is continuing to quote, in fact, you notice my last line, I said the fluid mechanics equations can be derived from them. So that's really our point of contact. Well, here's what I meant by a field variable. This is actually, this was actually for an electrostatic potential with a charge distribution rho, but it wouldn't matter where it was a gravitational mass or a magnetic field or a source in the potential flow of fluid mechanics. But the equations are basically the same. It's basically a Laplace's equation with something on the right-hand side. For gravity, it would be just G times the mass distribution, or 4 pi G times the mass distribution. And you can see why Einstein got this idea, because he's looking at this picture. And instead of thinking about it as a space, that, well, how do I want to say this? His big idea was space itself being deformed by the very presence of this object at the bottom. So that was, instead of saying, hey, there's a force acting over a distance, it's actually space deforming and making me feel as though there were a force. It's the same thing that happens on a roller coaster. It basically is you're moving around this curved surface. Gravity, you feel gravity going and starting and stopping and increasing and decreasing. Okay, so that was really a great breakthrough. In fact, my idol Feynman said, I'm pretty sure that I could have thought of special relativity. He said, and this guy got a Nobel Prize for inventing electrodynamics. He says, I'm pretty sure I'm at least as smart as Einstein, and I could have thought of special relativity, or somebody else would have. He said, general relativity. He said, I'm not so sure. That was truly a unique insight. Well, okay, that's the background, okay? If you're a physicist, you knew all that, okay? There have been a lot of solutions to these equations, and they've been very successful, and you've heard them in the news a lot. Almost everybody knows about light bending around the sun and how masses bend light. If you've studied physics, you probably heard about this so-called perihelion in the orbit of Mercury. Mercury could never quite be explained with Newtonian gravity, but when you put in Einstein, you got an extra term, so you could explain why this orbit keeps changing slowly. Gravitational lensing has been really a lot in the news recently because it turned out that you can actually, there was one example that was shown where you could see a star, you could see two stars where there was really only one star, because as the light came, there was a star blocking a star behind. So as the light bent, it came to us, it came around both sides of the star. That's among other things called gravitational lensing. And then we've all heard the big news in the last year about they finally were able to detect gravity waves, you know, by detecting explosions of supernovas and measuring all over the world with these incredible experiments. In fact, they got the Nobel Prize for it. Well, so we know about that. But those are all solutions to Einstein's equation in normal form, okay? Because our problem is we're dealing not with these equations for which these solutions work perfectly. We're trying to deal with equations that apply to this continuum of millions of galaxies. So this is really exactly like our turbulence problem. You know, we have no problem. If you take fluid mechanics, which many of you have, if you take a fluid mechanics course, they give you solution after solution after solution. The whole book is full of solutions. Massive books, if you look at some of the old books. What they don't tell you is that that's all of them. There aren't any more. It isn't like you learned a technique that you could solve another problem. That is actually the catalog pretty much of all the known solutions. Now, of course, CFD has expanded our capabilities enormously, but you basically have learned how to make solutions for existing problems for which that method only works for that problem. Now, that's, but that's how fluid mechanics used to be taught. And unfortunately, we've actually lost something by not teaching it that way anymore. But now we have these powerful numerical tools, but don't ever forget there's a lot to be learned from those analytical solutions. Okay, these examples I gave of Einstein's equations are those kind of solutions. The solutions at the bottom are a very different kind of problem. So now we're talking about basically a problem of averaging these Riemann equations. Now think about what would the average of that top equation look like? You say, well, what would you average? You can't average over time. You can certainly average over space locally, but the way you think about it theoretically is you imagine millions and millions of identical universes, each as a random variable. So in the sense when the kind of average we're really talking about is as if you had a million universes and you could add them all together. Okay, that's what we mean when we talk about average theoretically. Now, in practice, what it means is we've got to average locally. And this is a terrible problem because what's local? You know, well, do we look 100 light years away? Do we look a million light years away? Do we need to look a billion light years away? But in order to, the kind of equations we're talking about is as though we were averaging this over space locally, so we can talk about this millions of galaxies as though they were a continuum. Okay, now look, those equations, as Dirac points out, are highly nonlinear. What that means is there are lots and lots of average moments of fluctuating products. This is the turbulence closure problem. Right? It means you've got 64 equations to start with, but now you start averaging the products of fluctuations and the triple products of fluctuations. And now, you know, we complain when we have 109 equations to solve with a fourth order closure, right? I mean, imagine what a fourth order closure would look like with this. I mean, we're talking to hundreds of thousands of equations to try to solve. Right? People in the industry say, oh, we can't be bothered with Reynolds stress modeling. It's too complicated. Okay, imagine trying to solve the atmosphere or the universe with this set of equations. Okay, so what do? Well, we just try to plug ahead. Let's look at what we do in turbulence. Let me make sure I don't get ahead of my story. Okay. Well, okay, let me get a drink of water here. There are billions of galaxies. They're all contributing to this stress energy tensor. I've got to make averages on the left-hand side of the equation. There are billions of perturbations. So we literally have, even when we make these averages, we have a whole bunch of terms. Now, the good news is, maybe the good news is nobody's really done this very well. The bad news is that the best we can do, sorry?
Can you stay close to the camera then?
Uh-huh.
As much as possible.
Is there a camera?
The camera is near the monitor.
Oh, okay, I didn't know that. Okay, anyway, the problem is, okay, we have to decide what level of approach we want to this. And the way we really do it is almost we're going to treat the universe, and so it's the averaged Euler equation if you're a fluid mechanicist. Right, we're going to throw away all these products with nonlinear terms. We're just basically going to take, u du dx plus the u dv du dy equals minus the p dx. And of course, we'll fight the gravity term and we'll have an unsteady term, right? If the universe is not steady, static. Okay, in fact, people, this is interesting. People say, oh, Einstein was so brilliant. Well, yeah, he's brilliant to devise this equation, but the only solution he could think of was every term was equal to 0. I mean, and of course that's an accurate reflection pretty much of where we are today, okay? All right, let's proceed. Well, here's what we've done before, okay? This is the state of the art as I understand it now. And interestingly enough, the best idea they had was a guy 100 years ago. And a guy named Friedman, who Alex Friedman, yes. No. Anyway, he found this solution to Einstein's equation shortly after Einstein proposed them. And he sent it to Einstein, and Einstein just pretty much ignored it. And unfortunately, he was gassed in the war. He was a German, and he was in the German army, and they were, British and the Germans were gassing each other, and he died, and that was the end of him. But about the same time, or shortly thereafter, there was a Catholic priest of all things, who was in Liège, in Belgium, and he found a solution. He wrote to Einstein, and Einstein kind of blew him off. In fact, it wasn't, Einstein actually called this his biggest mistake, not realizing that his equations were saying that the universe was static. Because Einstein basically said, hey, I think all the stars are fixed in space, which was what everybody believed. And Lemaitre and Friedrich were the guys who realized that, hey, this solution is saying the universe is not static, it's expanding. Okay, and this is basically how they put this solution together. This is the metric tensor. So here's time, here's the speed of light, and actually this is actually the metric. This is distance. This is time, and this is space and spherical space. Okay, a solid angle. And the trick was to let space expand. And that's what this coefficient is all about. So basically, you now got the problem set up to try to solve it. And in fact, they did. And this was the solution. Now, remember, this was 100 years ago. And they just started plugging into that Riemann tensor, calculating all the terms by hand. It was a pretty simple problem, but even think of it, a 64 member tensor is not trivial, especially if you didn't realize at first glance that it reduced to like 10, but even trying to deal with 10 equations is a lot, and all the Christoffel symbols. So it was really a monumental achievement for the time, and even today to try to do it by hand is a problem. Anyway, you got to calculate all these terms in the Riemann or the Ricci tensor and the Ricci scalar, and you notice what they involve. They're all these second derivatives. Here's a double dot, so that's the second derivative of this expansion coefficient. Okay, so you can see if a double dot is 0, that means the universe is not accelerating, and if a dot is 0, it's not expanding. Okay. Now, Einstein ignored this because he didn't believe the universe was expanding. In fact, he didn't really acknowledge the problem until he was at Caltech for a big meeting after they built the Keck telescope. And the guys at Keck said, hey, look, the universe is expanding. Everything's moving away from us. Anybody know the name of the guy who headed that research group? Hubble. Well, in fact, Hubble realized that his group, I'm sure it's always a group, right? But one guy gets all the credit, but it's really a group, okay? It was really Hubble who could see these stars for the first time far enough away, and he realized that he could correlate how fast they were going by measuring the Doppler shift with how far away they were. And he, by using parallax and other tricks, he got a pretty crude approximation to distance. Okay, so that led to the so-called Hubble constant, that the rate at which they're moving away is proportional to how far away they are. And Einstein actually was at Keck with another great Dutch mathematician named de Sitter, and together they wrote a paper saying, hey, we confess the universe is expanding. I should have known this all along. And immediately gives credit to another German guy, completely ignoring the work of de Sitter himself and Friedman and Lemaitre. Fortunately, history has been much kinder to those guys. And so now everybody talks about applying the FLRW, which is Friedman, Lemaitre, Robertson, Walker. So when anything you hear about cosmology in the news is most likely the result of applying this FLRW algorithm, which I've just described. Okay, well, everybody thought it worked fine. In fact, when I was a student, we actually had a seminar at night one time on, we had a Wednesday night seminar series while I was at Hopkins, and I can remember well the discussion over whether the universe was going to explode or whether the universe was going to end. They called it the Big Crunch. It was the Big Bang versus the Big Crunch. And the Big Crunch meant that the solution of these equations was all going to collapse to nothing. And you get, depending on how you set the equations up. So there were really two sets of equations that had to be solved, and here they are. This was basically, this is Einstein's field equation with those variables plugged in. And then this equation always mystified me. I had more problem figuring out where that equation came from. And I finally one day realized that equation is nothing more than rho A cubed equals a constant. It's amazing how intelligent it looks. This is the density times volume cubed. So what is that a statement of conservation of? It's assuming conservation mass. If you differentiate with respect to time, then you get this very complicated and intelligent looking equation right here. Equation 15, this is basically the derivative of that equation. So you build in already something that you probably had good reason to believe was true. Energy is conserved, mass is conserved. But the truth is, there's every reason to believe neither is conserved. So you've probably over-constrained the solution. That's my premise anyway. But it's well hidden in this camouflaged, very intelligent looking equation. It's really a very simple statement. Okay. Well, okay, that's enough about the solution. It became clear with Hubble and the Hubble telescope that this wasn't really working, and we had to do something to fix it. And I'll show you in some detail the data from which we came to believe that the universe, in fact, was not only was expanding, it was expanding faster all the time. It was accelerating. I mean, this has been the big problem of cosmology now for the last 20, 30 years, is what's making the universe expand faster? Now, we're no longer arguing about the Big Crunch versus the Big Bang. You know, we're just trying to figure out why the universe is expanding too fast. Well, we didn't really have a good idea. The only good idea we can come up with is dark energy. In other words, how do you get dark energy into Einstein's equations? Well, let's look back. Go back to the equation. I'm going to use the equation in this form, but Einstein and most people use it in this form. And this is kind of a bogus term here. Remember Einstein believed the universe was not expanding. Well, that would immediately make all the R's zero, because all those A's are all going to be constants, right? So all these derivatives are going to vanish. Okay, so he's left with basically 0 equals T. And he says, well, I know something's got to be holding things together. So he postulates this lambda, capital lambda times a metric tensor, which did not come out of the derivation in any way. It was just literally pulled out of the sky and said, there must be a cosmological constant there that's keeping the universe together. Okay, and he calls it his greatest mistake because at the time he died, he thought it was. But now we've discovered, hey, we got an even bigger problem. Even when we put in all the terms of the non-zero R's, they still don't vanish. In fact, it's pretty bad. So we need a cosmological constant which as a source of energy. So it's not just that we need energy to make it accelerate, we need a continuous source of energy. Okay, so you'll hear, oh, the cosmological constant has been proven, you know, we all know that dark energy exists, okay? Well, okay, that's pretty much the state of where we are when I was listening to the radio that night. Now, there's a totally different problem of dark matter. Okay, I'll say a bit about that in a minute. But let's proceed. Okay, so here's the picture. You can see this. I stole this from someone, but it's in many books. Here's the big crunch. The universe all comes to an end at some point. Here's another idea that is growing parabolically. There's another idea that's growing energy linearly. And of course, here's the new idea that because of all this, it's expanding rapidly and growing exponentially with the mysterious source of energy. So this is where this is the state of the art now. Well, so we've invented dark energy to solve. We can't find it, by the way. We've never found a way to measure. Okay, but it's the only way to balance equations. I'll show you lots of examples. Okay, how about dark matter? Well, dark matter is a whole different problem, and I don't want to discuss it in this. And I'm not. I think I have a solution for it, but that's a totally different issue. Dark matter is the problem of trying to apply Kepler's laws to galaxies, and there's some interesting issues involved in how and what that means. But let's leave dark matter out of this discussion for now, because it really is a separate issue. But anyway, here's what the consensus of physicists is, not all of them, but here's the consensus of what people think the universe is known. At least it was a consensus last week. You never know for sure how fast it's changing, okay? It'll probably change really fast with this new telescope. Okay. So the universe is 68% dark energy, 27% dark matter, and only 5% things we can actually see and measure. Now, I used, it's interesting aside back here, Dr. Sadar became infamous at a famous APS meeting for reminding the audience that if you didn't conserve at least 80% of the momentum in an experiment, you probably didn't do the experiment right. So I used to hold my students back for years trying to make the equations balance if they missed by more than 10%. I mean, think about it. What does it mean if you integrate the momentum equation and your measurements only give you 0.8 instead of 1? Well, it's 2 points. One is Newton's law could be wrong, in which case you immediately get the Nobel Prize. Or number 2, you measured wrong. Or number 3, you didn't do the experiment you thought you did, which in fact usually the problem. You thought you were doing an experiment in an infinite environment and it knew how big the box was. CFD people have this problem all the time. Where do you put the walls? Okay, anyway, but now we're talking 68% missing stuff. Well, my whole life has been objecting to missing stuff as a solution to a problem. Just because you name it doesn't mean it exists. But let's see if there's a better idea. Okay, well, here's the right idea from trigonometry. We have these impossible equations too. They're not quite as impossible as Einstein's field equations, but they're pretty much impossible to solve. I mean, there really are almost zero solutions to a turbulence problem, other than artificial closure. But we have some incredibly good similarity solutions. What did we do? We basically used the fact that these equations are so nonlinear and things behave so nonlinearly, they just go to an attractor or some form and they kind of organize themselves for us. Now, my best example is you blow out your mouth on a cold winter day and you see this jet. And everybody says, oh yeah, that's a jet. What do you mean it's a jet? It's completely random, the flow is going everywhere. Well, you know it when you see it, right? It was a jet. And the fact that it had organized its way in such a nice similar way means you can cheat. Now you can go look at those equations and you can say, oh, I can see this is a parameter, that's a parameter, this is a parameter. I maybe or maybe not have enough parameters to make a dimensionless group. You apply the Buckingham pi theorem. If you only got one parameter, you say, hey, I got a solution. And in fact, almost every known solution in turbulence is that kind of thing. And it works because it's so nonlinear. The best example I used to give of highly nonlinearity is an FM radio. Try tuning off channel. You hear that, everything's digital now, so you don't hear it anymore. But in the old days, when you tuned off channel and immediately you went, right? What was happening? It was just taking whatever noise is present and blowing it up to infinity effectively. Okay, that's nonlinearity, but that's what turbulence really is. Turbulence is the nonlinearities are so strong that they just start dominating and exchanging energy all over the place. But it organizes itself by the equations allow it to organize itself into this, we'll call it for want of a better word, an attractor. Okay, so that's the way we solve most turbulence problems. And these methods have been around since the 1920s. Well, my big contribution to this was about 1986. I was teaching a class and some kid in the back of the room said, I don't see how we can just assume that. And by a series of serendipitous discoveries, we discovered that in fact, these solutions had a residual dependence on initial conditions. And that was a big breakthrough. I was asked at lunch today, why don't we rewrite Tennix and Lumley? The whole premise of Tennix and Lumley's turbulence book is that turbulence is asymptotically independent of its initial condition. So I had the unhappy position of realizing that I had disproved the fundamental premise of my thesis advisor's book. And I was at a meeting where I first presented this. And everybody went running back to tell John Lumley, Bill George said, this is all wrong. And in fact, for about 10 years, John Lumley and I didn't really speak to each other. And then we both ended up at a meeting in Switzerland in the late 80s, well, about 10 years later, actually, 98, I guess it was. And as I was presenting this, and a group of Russians were giving me a really rough time. And as we left to go to lunch, I was the last one out of the room, and John Lumley fell and stepped behind me. He had been waiting behind the door. And John's a pretty shy guy, but as we were walking to lunch, he said, Bill, you handled those guys really well. I said, oh, that was nice of you. I was waiting for the next shoe to drop, and he says, and by the way, I teach chapter 4 in my book, Your Way. So that was the ultimate compliment. But it was a recognition that these techniques we use have a lot more information in them than we previously believed. Okay, so what's the fix here? Well, the fix is, our problem is ideas get frozen. I'll just skip over this now, you can read it on the web. But we get frozen on ideas, and even when somebody finds a better idea, the book's still there for hundreds of years, so people just keep reading the book. Okay, well, let's design a new theory as though we were approaching this as a turbulence problem. What do we want to be true? Well, we know lots of evidence the universe is flat. You see it all in parts and thousands. The universe is spatially flat. It means no matter where you look, it's the same. Okay? It's also, let's mathematically assume that it's homogeneous. If it's homogeneous, it has to be infinite. You can't be homogeneous without being infinite. Okay? Let's imagine that atomic clocks work. Okay? And We know from Einstein's special relativity that clocks speed up or appear to speed up, and the clocks appear to slow down. Maybe they do, maybe they don't, but whatever, you don't get the right answer if you don't pretend they do, okay? But let's imagine them atomic clocks work and they don't change. They don't change. We change, our space changes, but the clocks don't. And the other idea is our reference frame should be Minkowski, and that has very special meaning. It basically means that the equations of Einstein's special relativity are correct. And then let's really make a big leap here. Let's say that mass and energy might not be conserved, right? And why would you, that's heresy. Well, look, we're missing 95% of it. So we can hypothesize a mysterious source we haven't been able to find after 30 years. Or doesn't it make sense to say, well, maybe that wasn't the right equation to go straight. Maybe mass isn't conserved. Maybe matter is conserved, but some property other than energy or mass that we measure is the thing we call mass. I mean, what do we call mass? I mean, mass, think of this guy, ma equals F. We apply a force, we measure the acceleration, we call that mass. But suppose the clock wasn't running right. Right, then you're going to get a different answer. And this is what we're saying here is, hey, maybe the clock that we thought, this atomic clock, was not the right clock to be measuring the effects of Einstein's gravitational theory. Okay, so this is really a significant change, right? Now, I was really thrilled at the same when I was really thrilled to find this. After I'd wasted about 4 years on this, I found this wonderful interview by Paul Dirac, the father of quantum mechanics, of relativistic quantum mechanics. And he says, I believe the times and distances which are to be used in Einstein's general theory of relativity are not the same as the times and the distances provided by atomic clocks. There are good theoretical reasons for believing this is so, for the reason that the gravitational forces are getting weaker compared to the electric forces. Wow. I mean, I felt I died and gone to heaven when I saw this. I said this was exactly what I'm trying to say. So now let's ask the question. Let's open a general question. Can we find a solution to Einstein's equation, which in one frame, atomic clocks work, everything is nice and Cartesian. Minkowski's it's a Minkowski space. But in this other space we live in, we only think the clock runs that way. And we only think space is like that. Okay, so we're living here, and this imaginary space is over here. Okay, that's where the similarity theory comes in. Okay, well, okay, let's hypothesize it. We'll have two spaces. I'll call, I think you probably can't see the top when I do that. There we go. Let's call one space tau and eta, and that will be our Minkowski space. And we'll call the other one T and X, the one we live in. Okay. Okay. In this tau eta space, this is actually the Minkowski metric. Okay. And this metric tensor is really very simple. So it's Cartesian minus 1, 1, 1, 1, 1. The one you're used to work in three spaces, just be 1, 1. You throw in the time and the physics and relativity, and it becomes a minus 1, 1, 1, 1. Okay, so it's just a diagonal tensor with all ones except the left corner is minus 1. Okay, so that's Minkowski space. Now, how are we going to relate this to our physical space? Well, this is exactly where we solve similarities theory. This is exactly how Luciano Castillo approached his thesis. This is exactly how people really for 40 years have approached similarity theory. Let's hypothesize a link scale relationship that takes space and divides it by some unknown link scale. It's a function of time. So here's the new piece. We've got this new link scale. This scales everything. It's kind of like the A in the old theory, okay? But the difference is we're also going to allow time to expand. Right? So not just space expanding, it's time expanding and stretching, being stretched by the same length scale. Okay, now remember, we live in the XT space, but we think we're living in the other space. That's the basic premise. Okay, now from here on, it's just plug and chug, really. You just calculate this big metric tensor, and then here's again where I had to spend the whole year learning how to use Maple. That was actually the hardest part of this problem. That's the part of being 77 years old. You just didn't really learn these things back when you should have, okay? And it was easy when you had good PhD students and you'd say, hey, go run this calculation for me. Hey, check out this. And suddenly you retire and you discover, holy smoke, I don't know how to do anything. Would you believe I actually got a big grant? I got a big grant from the EU. It was part of the grant was you had to say that you were being re-educated. And that was my proposal. I said, I'm retiring and I don't know how to do anything. And they said, yeah, I could imagine the 16 professors sitting around the panel having this, and probably everyone was saying, that's me, that's me. And I had the highest rating I ever got on a proposal, but I basically said, I don't know how to do anything. So my advice, try it sometime. Anyway, okay, this is the metric tensors. They're contravariant, covariant forms. So this is just math, okay? You can diagonalize it, but if you do, you kind of lose the important pieces, and I'll show you in a minute. What's interesting, physicists love to talk about proper time. And in fact, it turned out by actually the mathematics dictates it, what we assumed to be tau and its relation to t is in fact the proper time. And proper time basically has to do with whether you're following a, what's the word I'm looking for? I'm missing a word. I have more trouble with this word. Gunnar's always correcting me. It means you're following the optimal path. There's the word geodesic, that's right. If you proper time along a geodesic means that's basically the minimum, that's the optimal path through space. That's the way light waves go, for example. Okay, so it turned out when you solve all these equations, it turned out at the end, you get length scale has to be like the speed of light times time. Wow. People say, but that's the size of the universe. This universe is infinite. This is the size of the length scale. It's, think about it, if you solve a problem in turbulent jets, the length scale grows linearly. If you solve a problem in decaying turbulence, it goes like roughly the square root of t or some power very close to it. Okay, in this case, it turned out the length scale we hypothesized, the only solution that satisfies all the equations is one that grows linearly. And you could pick a coefficient in front of it if you want, but why not? Let's just call it CT. Most people say this is the size of the universe. And it's surely the size of the visible universe. It's the universe I can see if I look back in time. But you realize the universe you see is different than mine because you're starting in a different place. So you're seeing, you can look back in time from your location and you see a big ball out there that's CT, and I'm a couple, 10, 20 meters away from you, I see a different ball. Okay, but that's the length scale. Okay, it has no significance other than that. All right, and it also turned out you can actually solve for the velocities, and the velocity. This is I think I forgot to mention as we went by. In our hypothetical universe, it's at rest. Okay, so in our similarity coordinate system, tau and eta, nothing is moving. Everything is fixed. So we're actually expanding the coordinate system with the universe. Okay, but now in this other system we live in, it looks to us like, oh, everything's flying away from us, right? It's expanding. So that's the beauty of a similarity solution. You put yourself in a coordinate system that is effectively at rest. Okay, and it turned out this is exactly the length scale we do. Now, let me ask you, if you go back to Einstein's equation, you only have two parameters. You got the speed of light and you got the gravitational constant. There's no way you can get a length scale out of that. In fact, with those two parameters, you can't pretty much get anything on dimensional grounds. So the only way you could get a length scale is to put C together with time, and you could have gotten this answer by just dimensional analysis. You didn't even need to use equations. You could have said, well, there are only two parameters of the problem. The length scale ought to be CT. What else could it be? And I don't know a better answer than that, actually. Okay, let's just keep going. If you run through all this, you can eventually show that the relation between tau and t is logarithmic. And in fact, this one is growing exponentially relative to that one. This one's growing logarithmically. So just take the logarithm on one side or the other. What it means is that the atomic clock time appears to be growing exponentially, or the length scale appears to be growing exponentially in the atomic clock time, but not in the time we live in. I can see there's a real problem here, right? One time is running linearly by this clock, and the other one's behaving very differently. Okay, well, okay, you can play with Maxwell's equations. That turned out to be extremely important. And in fact, this is interesting. It turns out since Maxwell's equations, the Maxwell's equations dictate how light propagates. In fact, they pretty much dictate how everything propagates. It turns out, since they're linear, they look exactly the same in both coordinate systems, but the source terms look different. You can see this delta shows up. If I move from one coordinate system to the other, the delta shows, that length scale shows up in my source terms. And that's turned out to be extremely important, because what it turns out, a consequence of that is that the solutions from if a star radiates light, it doesn't matter which coordinate system meant, you get exactly the same answer. If you didn't know the universe was stretching and just measured the light coming in, you would get the same answer if you applied all this theory. Now, the problem is almost everybody in the field mixed it. They correct one part of it, but not the other part. And we'll see that has profound implications. Well, okay, everybody talks about Doppler shift. Turns out you can work with that, and you can show exactly how the light ends up getting, as we move toward us, it gets redshifted, meaning the wavelengths get longer. And then now, so I can pretty much wrap it up pretty quickly by showing you some results. Okay. How does the old theory work? Well, there are literally hundreds and thousands of measurements, hundreds and thousands of hours of telescope time and processing data. And it turned out the best the astronomers can do with the theory they have available is they end up concluding this is the density ratio to what they think should be out there. By the way, there's a concept called, there's some critical density. If you don't have that much mass, the whole universe collapses. But they can only find about 30% of it. Well, what's our theory say? Well, it's interesting. Our theory says there's no such thing as a critical density. So whatever you see is what's out there. So there really isn't any missing matter. The astronomers did their job very well. They probably did find all of it, or most of it. It was a theory that was wrong. Hubble's another big problem. This is a very recent paper from the Journal Astronomy Journal. And all these curves are different solutions to the observations of the so-called Hubble parameter for different amounts of dark energy. And you can say they go all over the place. You can pretty much get any answer you want from 20% dark energy to 90% dark energy. On the other hand, what's our theory say? It actually says it's a linear relationship. There's a linear relationship between the Hubble parameter and this Z parameter, which is the amount of redshift. It turned out it's actually pretty insensitive. It turned out our best choice of Hubble was so-called 63.6 kilometers per second. The generally accepted value is about 67. There are numbers that go as high as 72. But if you notice, this red curve is the 67 value with our theory. The blue line is the optimum value from all the data. And it turned out if you use our data, the universe is 15.4 billion years old. If you hear that you've heard the 13.8 number, it's based on the theory I just showed you that doesn't work very well, assuming 70% dark energy. And so this is really significant. It's an extremely simple relationship. We can ask about the cosmic background. This has also been taught. This is part of why your TV has hash in it, or at least did before they became digital. This is the first universe that we could see. When the temperature dropped to 3,000 degrees, photons could propagate, and we could see this picture. And this is actually the picture taken by looking all, and the astronomers will say, well, the small fluctuations, so it must be acoustic. The turbulence person looks at it, so that's what turbulence looks like. That is turbulence. The whole thing is probably turbulent. And that it started as a big turbulent process at the Big Bang. In fact, interestingly enough, our solution gives exactly the same answer as the old theories. And the big reason is you measure the spectrum, you try to infer how it got stretched over, redshifted. And there's some interesting things here. If you work back to when this happened, you get a number that's about 10 to the 60th times the smallest scale that could have ever existed in the Planck scale, 10 to the 60. And if you go to the present time, you get another 10 to the 60. So in fact, our theory gives almost exactly the observations. There's a lot more I could say about that, but this is really the slide that's crucial. This is the reason we believe that the universe is expanding. This is people got the 2 Nobel Prizes for this. What they looked at was whether the universe was expanding. But all their data in this picture, this redshift is the horizontal parameter. The redshift, all their data has been multiplied by 1 plus c. Look what our data looks like without multiplying by 1 plus c. It's almost a perfect fit. Anyway, I think I can pretty much wrap it up. Here's where I want to get to, though. I want to show you this picture. Our theory basically says you can go all the way back to the beginning. One of the craziest numbers in the history of physics is the so-called, it's called the worst prediction in the history of physics. You can Google it, worst prediction in history. And the problem is it's off by 10 to the 120th power. This is the amount of energy the quantum mechanics calculation was put into the beginning. And compared to what's there now, it's 10 to the 120th power. So it's truly called the worst prediction in the history of physics. Well, what does our theory say? Our theory says it's actually the best prediction in the history of physics. Because if you take our theory and the present measurements and you work it back, guess what? We get almost exactly that number at exactly the Planck time. Actually, it's the Planck time of 5. You really don't get any better than this. That's 120 decades of data over 15.4 billion years. Now, you could say, well, there's no data points in between. Yeah, well, that's true. The problem is our entire existence is pretty much inside that little triangle. So what we really need is astronomers who can push back into these earlier times. But that's, again, almost impossible because it's only visible in times like this. Well, okay, I think that's probably, let me stop with this slide. This is a wonderful picture. If you ever get to Brussels, make sure you go to the Hotel Metropole. And this picture is actually hanging here. It's quite small. In that picture are 17 people who later won the Nobel Prize. That's a pretty impressive group, huh? And of course, right here in the middle is Einstein. And Einstein had terrible problems with relativity and turbulence. There are many jokes about, he says, when I die and get to heaven, I'm going to ask God about turbulence and quantum mechanics. I think he might know the answer to quantum mechanics. But anyway, what's funny is that this is the meeting where Einstein made his presentation, and said, God does not roll dice. I'm sure most of you heard that statement. And Niels Bohr, of course, of the Bohr atom fame, who is a great advocate of quantum mechanics, he says, stop telling God what to do. And my response is, well, maybe God did roll the dice at least this once. I think it will be one of the great ironies of history if my solution to Einstein's field equations proves the Big Bang had its origins in quantum mechanics, which I think is really pretty funny. That would be a great joke on, if Einstein could still look down, I have a feeling he would, I'm not sure he would see the humor. It's a good place to quit.
Thank you, Bill. So I would like people to ask you a question. No, it's perfect. I know there are people who may have questions, so either in the audience or here in person. Any question for Bill? Yeah, yes.
So I guess I have one question. So I guess, have you thought of this from a statistical mechanics point of view, where you could think of basically, remember we were talking in the very beginning about space and time averages and how each of the particles in space can have. So I was thinking, like, could you think of like a virial theorem where you can think of like how, I think that's the statistical mechanics.
Actually, I wrote a paper about the earliest version of this. I tried to consider the virial theorem. And the problem is, the way I'd love to use the results from applying the virial theorem. In fact, I had a slide showing some of that, but the problem is it basically assumes conservation of energy.
And that's the thing that is not actually being conserved.
Yeah, that's exactly right. So it's actually giving the wrong answer. And of course, that's why you need dark energy to fill up the gap, right? But in this paper, that was actually published in a rather strange journal called Journal of Cosmology. What I tried to do is ask, how would the virial theorem have to be changed if you didn't conserve energy? In fact, in this case, suppose this were not dx dt, let's say, or that. But suppose it was dx d tau squared, where tau was log t. And you can see what it's actually going to do, instead of everywhere there's a mass, you're going to get a t squared times the mass, or t is the age of the universe. So the amount of mass you think is out there is proportional when you looked at it, right?
It depends on the time, it's a function.
That's exactly right. And I think that I didn't need that. So that's what set me off on this track. But I realized that, in fact, I really needed to approach it from, nobody was going to believe it if I just start with Einstein's equations themselves. But in that Journal of Cosmology paper, I actually went the other direction. Yeah. And I kind of didn't know any relative to it. But it was really interesting because the virial theorem was a very important part of it. And I do think it means, let me put it this way, every problem I've ever worked on like this, I was never able to convince my colleagues that it was reasonable. It's only when the kids take it, you being the kids, right? If the kids say, in fact, I left the slide out, but my colleagues say, oh, it can't possibly be right, or somebody would have thought of it. Somebody smart would have thought of it, that's right. And the kids always say, what's the problem here? It's obvious. And so, in fact, there's a wonderful statement from Feynman about my hero, about, well, why did it take 30 years for quantum mechanics to be accepted by most physicists? And relativity, by the way. You know what the answer is? It took 30 years for all the old physicists to die. Now, people say with me, we have a number of papers that took 8 to 12 years to get published. In fact, I have the record for the longest time between submission and acceptance at GFM. And the reason people say, why did it take so long? I had to wait for all the reviewers to die.
Any other questions? Who has more questions? Because I want to engage more discussion. That's why I'm interrupting you. So basically what you're saying is that, okay, the universe is expanding. but then it's not accelerating, it's decaying.
No, it's
velocity.
actually decent. I didn't, but he got a little rust there at the end, but let me show you this
I was not,
picture.
you were not rushed. You were-
Yeah, no, I was looking at the clock, and I know some of you need to leave. But if you look at this picture, this is our theory. These were the supernova data. And you can see this is right out of the Nobel Prize winning paper. Yeah. These are right out of the Nobel Prize winning paper, okay? And you can see all the various simulations for various amounts of dark energy. And they say, well, it must be this one, which is about 50 dark energy, 50% dark energy, 50% matter. Okay? Now, and by the way, they multiplied this data by 1 plus Z, which of course is going to tip the curve up. And the answer is why, you guess, why did they do that? Well, they had good reasons, they thought, but look what the old theory says. Here's what our theory says the distance away should look like. And this is what the old theory said. If you don't multiply it by 1 plus D, the data looks awful, right? But in this picture, we used the original uncorrected data. That's the best fit on the left. The only parameter in this is that Hubble constant we determined with that linear fit, and the so-called absolute magnitude of the star, which is a whole different ball of wax, or a ball of worms, but the absolute magnitude of the star for a supernova is believed to be pretty much what the Sanders-Sakar limit is. And the generally agreed upon data number is pretty damn close to the one we used. We again came up like 18.5. I mean, that to me, this isn't a log plot. This is a linear plot. I mean, I don't think it gets any better than this. And that's decelerating. The only reason this accelerates is because of the correction. The Maxwell's equations, I think properly argued, say shouldn't happen.
That's a very good point.
But
So
I
it's expanded. No, but I do think, does anybody in the audience would like to ask a question? Because I do think these are these discussions that we could learn a lot.
You can see notice how this curve bends up on a log plot. That's the acceleration they think they see. Ours goes the other way.
So maybe in the conversion in the space, remember you were converting from once at time, and so that means at the beginning the space and time is growing exponential in the
depending on which one you're looking at. Okay, but by the way, here, interesting question. If this is also obvious, why didn't we know the difference? Well, look, I didn't get to this slide, but it's by the way, all this is on the web now. This presentation's in my website, turbulenceonline.com, and this paper has been uploaded as well. The paper that these are taken directly from. And look, you can ask the question, do you know that what was the difference between log time and linear time? How can we tell? If you start measuring at the time of Galileo, okay, when we first started doing science, the leading error term between the log time and our time, or the linear time, is 3 times 10 to the minus 8. You couldn't have possibly detected it. There's a 1 second difference over the entire human existence. It's only when we start looking back billions and billions of years that this T here starts making a huge difference. Then we see the differences. So, anyway.
Yes, Jonathan.
I guess we're saying mass and energy are not conserved, and our control volume is the infinite universe. Where is it going?
I knew somebody was going to ask that. Thank you. Where does temperature go? Where does pressure go? We don't ask this question, right? Why don't we ask this question? It's not a conserved quantity. Right? It's a real quantity. It measures something, but it's not a conserved quantity. So it's measuring. In fact, you can actually show that the energy and density goes T to the minus 2 or E to the minus tau, 2 tau. but it's not a conserved quantity. And by the way, it's really good theoretical, it's not even debatable. If you pick up any good book on cosmology or general relativity, there's something called Noether's theorem. Most physicists have for sure heard about it. But Noether's theorem basically says the whole concept of energy conservation is because you have discretized time in equal increments. You choose to discretize time differently, you get a different conserved quantity. In fact, our conserved quantity turned out to just be c squared over g times delta squared. That's the conserved quantity. Anyway, is that a good answer?
I mean, I don't know.
It's it makes you feel uneasy, right?
Well, I know in quantum mechanics, people observe particles popping in and out of existence. So, maybe that could be. Well,
but you guys, all that is before the time we're talking. I mean, gravity only comes in about, well, the so-called Planck time, right? And which is like 10 to the minus 44 seconds. Think of this is a theory that goes from 10 to the minus 44 seconds to 15 billion years. The numbers are mind-boggling. But anyway, gravity effects come in. The Planck properties basically are the measure of when quantum mechanics knows that gravity's around. So all those things you're talking about are way before. Well, way before. They're between 10 to the minus 43 and 10 to the minus 99 or something.
I think you brought a very good point, and we will end soon, but something that when you were discussing this homogeneity, the space is not a finite domain, then the questions are completely different. Talking about a finite domain versus an infinite domain.
Yeah, that's a really interesting point. When I was in high school, I moved to a town that had really poor education system. But the best thing that happened is they had a boatman builder that would come by once a year. And they had a book called 1, 2, 3 Infinity. I don't know if you've ever heard of it, but it was by a famous, I think it was Gamow. And in that book, this is high school, right? And it to me had a profound effect on me. But he tells about the tourists arriving at Hotel Finite, and they need a room. And they say, well, I want, the guy says, I'm really sorry, all my rooms are filled. But if you go across the street to Hotel Infinity, they might be able to help you. So he goes over across the street to Hotel Infinity, and the guy said, well, all my rooms are full too. But maybe I can help you. He said, I'll move the guy in number 1 to number 2, and number 2 to number 3, and 3 to 4, all the way to infinity. And you can have the first room. Okay? But then an infinite number of people arrive. And they say, well, I'm sorry, all my rooms are full. But he said, but I think we can handle it. He says, I'll move all the 1 to 2, and 2 to 4, and 3 to 6. So all my odd numbered rooms are now empty. So I have room for everybody. So in a sense, what happens in an infinite environment is really a very different kind of question than what happens in a finite one. Okay.
Thank you so much for your wonderful talk. I really appreciate that. Was a good talk. This was recorded.